we defined a sequence, this is an infinite binary sequence, is algorithmically compressible by a factor of s, means that if you look at the initial segments of the sequence, there are infinitely many initial segments, infinitely many L, such that the Kolmogorov complexity of the first L bits of x is less than or equal to the fraction s of L, s times L, up to an additive constant. Okay, so the x is algorithmically compressible by a factor of a half, means that for infinitely many initial segments of x, right, you can find a program that has half as many symbols in it as the length that you're considering, and that program runs and it outputs the initial segment of x of length L. Okay, so the information that's sitting inside the first L bits of x, right, has size a half of L. Okay? So an example of something that is algorithmically compressible by a factor of a half is a sequence such that every even bit is 0. Okay? The 0 part you can talk about just by saying, the even part is 0, that's C, that's the program. Right? And the odd part, well, you just have to say what the digits are sitting in the odd places. And that'll take you the length over 2. And so that's a not misleading example. Compressible by a factor of s means that there's a compression algorithm which will reduce the size of, it'll present the information x restricted to L, but in compressed form down to something of size s times L. Okay. And actually, interestingly, as a side comment, in this study of effective dimension and compression algorithms, computer science compression algorithms actually show up here, and they're useful. People use them to in the inner workings of algorithmic information theory. Okay, now, 2 theorems about this concept that are relevant to us today. So the first is if you have a singleton, right? We defined the effective dimension, which was an effective version of the classical description of Hausdorff dimension. The effective dimension of a point is the infimum of all the s's, such that x is algorithmically compressible by a factor of s. Okay, so if you can be compressed down to a half, well, you can be compressed down to 3/4, 5/8, etc. So take the infimum of all the compression factors that x exhibits, and that's the effective dimension of this singleton. Okay, the second theorem that I wanted to recall is if you have an arbitrary set. Yeah, so we're recalling 2 theorems. The first theorem was, the first thing is this definition. A point is algorithmically compressible by a factor of s, means there is a computation procedure, which you could think of as a compression algorithm, and it's on infinitely many initial segments of x, it compresses the information in x restricted to L, that's the first L bits, it compresses that information down to something that has size s times L. S is less than or equal to 1. Okay, so the second fact is that analysis of compression and effective dimension, right, gives you a criterion to tell what the Hausdorff dimension of an arbitrary set is. So this is not sort of an effective notion. This is the actual, classical notion of dimension. So if you have an arbitrary subset of 2 to the omega, the Hausdorff dimension of that set is given by this, right, the inf of the sup of something. Okay? So it's the infimum of all possible data sets B, all possible oracles B, the infimum over all B of the supremum over all the points in the set of effective relative to B dimension of that point. Okay, so you look at the infima, so as B has more and more information in it, okay, that allows you to do better and better compression algorithms. So take the inf over all B of how complicated do the points of A look? How well is it that you can compress all the elements of A? So if I look at the set of reals, right, that are 0 on the even bits, right, that set of reals, every element of that set can be compressed by a factor of a half. Right? But if you look at something that's random on the odd bits, that odd part can't be compressed at all. It's random. Okay? So if you look at the soup of that set of 0 on the evens, relative to any B, there's going to be some things that the odd part of that real is random relative to B, so it can't be compressed by anything more than a half. Okay? So for the set that is 0 on the evens, this gives you an easy calculation, right, of the dimension is, as you would expect, a half. Okay, so that's the thing that we want to keep in mind, right? The Hausdorff dimension, which we gave a topological, right, definition like Lebesgue measure, except there was this ingredient of looking at smaller and smaller scales, and there was a factor in the exponent of figuring out what the size, how are you going to assign mass to the different basic open sets. That definition is equivalent to something that's computational. It's based on a computational heuristic. Right? It's the computational complexity, the soup of the computational complexities of the elements of the set. Okay, good. So now, let's move to today's topic. Okay, so this is where we are. This is where we are in these talks. Right? We've gone through these first 3 topics, and today I want to talk about using this kind of computational heuristic to analyze dimension, to return to some of the classical geometric measure theoretic issues. How does dimension work? Right? Capacitability. Capacitability is the property that says if you have like measure, right? If you have a notion of size or extent of a set, the set is capacitable means that same property, right, whatever size or extent the set has, is supported by the size of its closed subsets. So if a set has positive measure, right, then it has a closed subset of positive measure. In fact, you can approximate the measure of a set arbitrarily closely by the measures of its closed subsets. So the simple sets, a set is closed. What does it mean to say that a set is closed? Right? Its complement is a union of open balls. An open ball, right, is determined by a finite sequence. Okay? So you could think of a set as closed if there is a process, right? And what does the process do? It looks at an infinite sequence, and it examines its initial segments, and if the sequence is not in the closed set, eventually it rejects the sequence. The points the sequences that are never rejected, that's the closed set. So a closed set is a very concrete that's a way to describe a closed set. Right? An open set. A set is open if X is in an open set, if and only if X is in one of the basic balls whose union is the open set. So at some finite point, you see that X is in. Okay, so an open set is something where you kind of see that an element is in the open set based on finally much evidence. Right? A set is closed if its elements, right, are the things that are never rejected, right, as you look along their initial segments. Okay, so there's a very concrete way to think about open and closed sets. Right? They are, as subsets of 2 to the omega, subsets of the Cantor set, they do have very kind of concrete forms of definition. Right? And capacitability says if you have an arbitrary set, right, its geometric its fundamental geometric constants, dimension or measure or so forth, are supported by the closed set. So it's got a closed core, a concrete core, and the rest of it is kind of ornamentation, little sparkles around it or something. But the real measure of it sits on something very concrete and solid. Okay, that's capacitability. Okay? So we want to investigate how does capacitability work for dimension, right? And we're going to use that heuristic of sort of the computational analysis, or the computationally motivated analysis of how dimension works to gain some insight. Okay, secondly, dimension, right, Hausdorff dimension, is based on looking at, we wrote it two different ways. One was a linear form of compression on a binary set, and the other one was a kind of exponential factor in analyzing the measures of basic open sets. And those 2 points of view are dual. They talk about the same thing as was mentioned in that theorem. Okay. There are a lot of other functions than multiplication and exponentiation. Those are fundamental mathematical operations, but there's lots of other operations beyond addition, multiplication, and exponentiation. And sometimes addition, multiplication, exponentiation are not sufficient to finally calibrate the dimension of an object. So normal Hausdorff dimension cannot calibrate the difference between a curve in the plane and a Brownian motion. Right? But those two things look quite different. The Brownian motion is all over the place. It's kind of filling in the space to a certain degree. And you can differentiate those two types of geometric objects if you take a more finely graded family of functions than the power. Okay. And that's what gauge functions are. Okay, so gauge functions are used to give a refinement of dimension. Okay, so we're going to talk a bit about that. And then there's quite an interesting phenomena which I call strong dimension, and that's where we're going to finish. Okay, so that's today. Okay, so here's the with that preamble, here's the situation. We noted that Hausdorff dimension, Hausdorff measures behave well in analytic sets. Okay? So analytic sets are capacitable. Okay? So whether that good behavior, if you look at these, there were theorems in the 1950s and 1960s that analyzed sort of the abstract, how does Hausdorff dimension work on arbitrary sets. Right? And a lot of the good behavior was proven for analytic, right? And then that's where the proof methodology broke down. With analytic sets, you have a presentation. They are a projection of a closed set. Okay, so you have a closed set is a very concrete object, and the projection function is a very concrete thing, and you can get a handle on how those sets work using the representation as a projection of closed. Okay, so now what happens if you try to go a little bit past analytic? What happens if you look, say, not at analytic sets, but at their complements? Right? The classical theorems don't cover that. The methods that were worked out in the 50s and 60s don't apply because they were explicitly tied to analytic representations of sets. Okay, so the answer, right, turns out to be tied to metamathematical features. It's something that I find surprising. Dimension is a kind of basic mathematical quantity. Right? These sets, complement of an analytic set. Take a closed set, project it, and look at the complement. That is a very concrete object. Right? Why should you go from being completely able to analyze the analytic sets to the co-analytic sets they involve the full-blown structure of the universe of sets? but that is the way it turns out. Okay, so let's see it. Okay, so to do this, we're going to have to extend the apparatus of logic, the apparatus of syntax, past the arithmetic form of definitions to analytic definitions. And this is where somebody asked the other day, what does the 0 refer to in pi 0, 1? Now, we're going to talk about what happens when 0 goes to 1. Okay, so a set is sigma 1, 1. If there is a pi 0, 1 predicate, a pi 0, 1 predicate is for all n, some recursive thing holds of the argument. X is in a pi 0, 1 class. Pi 0, 1 set is defined by X is in if and only if for all n something computable happens. Okay, sigma 1, 1 is X is in if and only if there exists an element of omega to the omega. So that's an infinite sequence of natural numbers. Doesn't have to be binary. An infinite sequence of natural numbers such that this pi 0, 1 predicate holds. Okay. So typical sigma 1, 1 set, it's the projection. Right? Something is in this set if and only if, think of x and y in the plane. So x is in, along the horizontal axis is in if and only if there exists some y such that x, y is in the pi 0, 1 set, which is a closed set. Okay, so this is explicitly of an analytic form. Right? Pi 0, 1 predicates are closed. So I have a closed subset of omega to the omega across whatever x is, if x is an element of 2 to the omega or x is an element of omega. Right? The same syntax applies. Okay, so I have a closed subset of Baire cross Cantor, for example. Right? And A is the projection on the Baire coordinate, B-A-I-R-E. Okay? So it's exactly the form that I said was a normal form for analytic set. Okay, sigma 1, 1 sets are analytic. The difference between a general analytic set and a sigma 1, 1 set is that this predicate is effectively presented. It's the set of paths through some recursive tree, some computable tree. If you allow R to be pi 0, 1 relative to a real parameter, you know, throw in an oracle, pi 0, 1 in an oracle, then every analytic set can be defined by a formula of that form. Okay, so sigma 1, 1 sets are the effectively presented analytic sets. And then you can repeat the same syntactic device that we did with the arithmetic sets. A is pi 1n. So sigma 1, 1 is effectively analytic. Pi 1n, if it's the complement of something, that's sigma 1n. So pi 1, 1 is the complement of a effectively presented analytic set. Okay? And generate the hierarchy by adding quantifiers over Baire. Okay. Sigma n plus sigma, oops, sorry, this should be a 1. I can fix that. There we go. It's better to do it on the screen than to do it up here. Keep that in mind if you ever have to give a lecture like this. Don't write it up here. Okay, so a set is sigma 1 n plus 1 if it's obtained by existential quantification followed by something that's pi. You can see cut and paste. Don't do cut and paste. I copied the slide from the arithmetic. Okay, so it's sigma 1 n plus 1 if it is obtained by existential quantification followed by pi 1n. So you generate the hierarchy just like we did with the arithmetic hierarchy, except the quantifiers are not over finite, they're over infinite. You can think of it as this is a quantifier over reals. Okay. All right, so as I said, if A is a subset of Cantor or Baire space or of omega, A is sigma 1, 1 relative to some real x, if and only if A is analytic. So it's a syntactic representation of the class of analytic sets. Okay? Similarly for pi 1, 1 and co-analytic. And if you don't have any real parameter, you don't have any external data to supply to the definition, then those sets, we say, are effectively presented. They're real concrete versions of analytic and co-analytic sets. All right. We're going to analyze the question of capacitability on co-analytic sets. Okay? Analytic sets have the property, if an analytic set has dimension d, then for every s less than d, there is a closed subset of the analytic set that has dimension at least s. Okay? So for analytic sets, the dimension of the set is carried by the dimensions of its closed subsets. Okay? We're going to show that that's, if you asked, do co-analytic sets have the same property? Right? Does a co-analytic, the complement of an analytic set, does it have the same property that its dimension is carried by its closed subsets? Right? We're going to show that the answer to that question is not determined by the axioms of set theory. Right? It's a natural question. And when we were first looking at that question, I thought, oh, good, right? This effective analysis of dimension, right, is going to open up. You know, it'll make some of these questions more accessible and make these concrete sets, you know, more easily. You know, I know something. You know, I know something that they didn't know in the 1950s. Mathematical logic has progressed. We have a good understanding of how dimension works in this kind of point-wise setup. So let's try to take these classical theorems and push them out. Right? Let's do better. Let's handle a wider range of sets. But it didn't work out that way. In fact, there's a very strong barrier against doing that, and this is it. Okay? All right. So now I have to, since the answer, the question is geometric, the answer to the question is logical. Yes, right? So to set up the apparatus to work on that question, I have to introduce what Gödel defined. It's the universe of constructible sets. Okay, so you can think of, here's an analogy, right? Among all the real numbers, there are some which are accessible. Right? There are some that you can get your hands on, like pi, right? Or square root of 2. Or more generally, you might say every subset of the natural numbers for which there's an algorithm to compute on input n whether n belongs to that set. Right? Those numbers are sort of, if I look at that set and think of it as telling me an infinite binary sequence, right? The digit is 1 at n if and only if n is in the set. Those sets give you a class of accessible real numbers, points on the continuum for which you have a real firm handle. Right? So the computable numbers, right, inside the continuum are special. They're the ones that we can work with. Right? Now, okay, and then there's theorems, right, like Liouville's theorem, right, that you could think, oh, the algebraic numbers are really concrete. We can work with those. Is there a number that's not algebraic? Liouville's theorem. Yes, there's a transcendental number. Right? Then, well, suppose I have countably many numbers that I think I can work with. If I have a method to describe numbers, the method is syntactic. There's each description is finite. I get countably many real numbers. Can I exhaust all the real numbers? Is every real number definable? Well, no, by Cantor's argument. Right? The set of real numbers is not countable. Okay? That same sort of thinking can be applied not just to numbers but to sets. Right? We could say, well, every finite set, if I take any like set which is hereditarily finite, it's finite, all of its elements are finite, all their elements are finite, etc. The whole thing, right? The membership relation, the whole process there, everything that goes into building up the set, right? That whole apparatus is finite. It's basically of a finite graph, right? Where the edge is a directed graph, where the edge is A is an element of B. Those things are super concrete. Right? The hereditarily finite sets, there's no ambiguity there. I mean, some of them are really big, but as mathematical objects go, they're quite concrete. Okay? The collection of all the hereditarily finite sets, okay, that's something that's infinite, but it's still pretty concrete. It is as concrete as the natural numbers are. And then what? Right? If you accept the apparatus of infinite sets and you want to work with the reals, you want to do analysis, or you want to do some kind of functional analysis, functions from reals to reals, you want to work with fairly, somewhat abstract, but not finitely represented mathematical objects. Right? Well, then it's interesting to ask yourself, what are the concrete ones? What are the sets that are there by virtue of the nature of set? Right? Just like the computable numbers are there by virtue of acceptance of finite computations. Okay? That's what Gödel worked out. Okay? So here's his definition. Right? The definition of the class of constructible sets. Well, the empty set. The empty set is constructible. Okay. Then, suppose you have, I'm going to do the build up by recursion now. Okay. So suppose I'm at some point in my recursion, and I've got all the sets that I've generated. Do you have a question? Or? Yeah, go ahead.
So, I think in the previous class we saw this method of assigning some measure to some particular subset of the reals, such that outside that particular subset,
yeah, the measure vanished out. The complement was given measure 0, right?
Can we define a measure on your constructible reals?
You can, on the constructible reals? Well, it's easy to do it if every set's constructible. Let's come back to this, okay? Because I'll show you we're going to be working with constructible sets. How the set of constructible reals sits inside the reals is not determined by the axioms of set theory. Okay, so the set of constructible reals could be a countable set. That's consistent. It could be everything. That's also consistent. So it's somewhat, it's fluid. And the answers to these kinds of questions depend on what you think, what is your concept of set? What do you think is happening with sets? Okay, so this is the phenomena of independence in set theory. That the actual concrete, I'll say a bit more about this in a second. Okay, so Gödel's constructible sets. The empty set is constructible. If I'm generating things by recursion, if I've got all the sets that I've constructed so far, okay, so it's step alpha. Maybe, it's step, I have all the sets I've constructed so far. For example, while alpha is finite, what we're going to be building up are all the sets, the sets that have rank. They start with the empty set, and then you get the set that has one element, the empty set, and then you get a set that has a couple elements, and so on. You're building things up for finite sets of finite rank. Right? When you get to the first limit ordinal, you take all the hereditarily finite sets. That's what you've got so far. Right? At limit ordinals, you just take everything you've got so far. Okay? At step omega, where you start to build something infinite, you're going to form the set of X such that X can be defined over this structure. using elements of the structure. So it's literally pulling yourself up by your shoelaces. And you take everything that you've built up so far, and using that, what else can you define? What else can you, in a simple way? First order definitions. Okay? So you look at what you can define, what you've given so far, you look at everything that you can concretely define using only what you've generated already, and that's what you have at the next step. And then you just keep going. Keep using what you've got to build what you can next. Then you use that to build what you can next, and then you use that, and so on. So that's Gödel's class of constructible sets. Okay? Now, let's make a couple of observations about it. Right? So the class of constructible sets is called L. Okay? So a set is in L. L is the class of all sets you build up this way. Okay? Every ordinal is going to, for example, every ordinal will be inside L. Every good enough. Okay. X is in L if and only if there's an ordinal beta, such that X is in L beta. So a set is constructible if there is a stage in this recursion at which we generate the set. So you can think of these steps as steps in constructions of sets. Right? A set is constructible if it's constructed at some point. Okay. The ordinals are well ordered. So if a set is inside L, there's a stage, a least stage where it enters. Right? The set of stages such that X belongs to L beta has a least element. Okay, so you say that X is constructed at beta if beta is least such that X is in L beta. So what did Gödel show? First, he showed that the axioms of set theory are true inside L. L is a model of the Zermelo-Fraenkel axioms of set theory. Okay, so that means, right, since L satisfies the Zermelo-Fraenkel axioms of set theory, it's not possible to prove, using those axioms only, that there's a non-constructible set. Right? Because in L, every set is constructible. L satisfies the basic axioms of set theory. So the basic axioms of set theory cannot prove there's a set that's not constructible, because L satisfies every set is constructible. Okay, so good. The second thing that Gödel proved was, this is a kind of consequence of it, but if you look at this way of generating sets, right, it induces an ordering on the appearance of sets. This set is constructed before that one. They're constructed at the same height, but this definition was simpler than that definition. Right? This way of laying out a collection of sets, right, it's definable. There's the definition, right? And it gives an order of construction that orders all the sets. So the axiom of choice is true, because you take any non-empty set, you can look at the element of that set which is constructed before any of the others. There's a global definable well-ordering which allows you to define choice functions or the Hausdorff well-ordering principle or things like that. The whole universe of sets has one definable ordering, the order in which things were built. Okay? And that ordering is well-founded. Okay? So the axiom of choice is true. Every non-empty set has an element which is definable in terms of that set. So it gives you a way to choose. If I have a map it's the axiom of choice is given a collection of sets, there's a function that chooses an element out of each one. Okay, how do you do the choosing? Take the one that was constructed first, each time. Okay, good. So Gödel proved that if the axioms of set theory are consistent, the basic axioms, then so is that set of axioms together with the axiom of choice. Okay. Now, if you look at how that order of construction works, right? And get into a little bit more deeply, you can conclude, and Gödel did, that if the class of all sets is equal to the class of constructible sets, if V equals L, then there's a sigma 1, 2 in the sense that we just described, right? Exists a real for all reals, something closed, right? Well-ordering of the continuum. And it's based on this order of construction. Okay. So yeah, go ahead.
And obviously you're defining some L alpha plus 1 minus L alpha. So how do you define in the same, if you're constructed at the same ordinal?
Oh, then you compare the definitions that were used. So if you're constructed at the same ordinal, right? So you order the formulas and you order the sets you've already constructed, right? And then, so now you're ordering pairs, formulas, and the parameters that you might use in a definition. You order that whole thing, right? And that gives you a well-ordering of all the new points. So they are ordered by the complexity in that sense of how they got into L, right? Okay, so there's a very concrete well-ordering in L, there's a concrete well-ordering of the Cantor space. That means all these sort of oddball examples that you can construct from the axiom of choice, non-measurable sets, etc. Right? All of those sorts of things can be defined. Right? There are definable examples of all of those sorts of things sitting inside L. Okay, so L brings the axiom of choice far down in the descriptive hierarchy of definable subsets of the continuum. Okay, so that's work from the 1930s. Okay, now, I want to turn to this question about the co-analytic sets. So the well-ordering of L is a sigma 1, 2. So we would expect in L, with the axiom of choice, right, there's going to be strange things are going to happen once you get past sigma 1, 2. Whatever you could do with the axiom of choice, you can do using this definition to make the axiom of choice apply. Okay. But co-analytic sets, those are pi 1, 1 sets. Right? That's below the sigma 1, 2. That's somehow a little bit below the radar of the well-ordering of the reals that you get inside L. Okay, so this is the set that we're going to look at. Right, this is what's called the maximal thin pi 1, 1 set. Okay, so first let's say what the definition is, and then we'll say what maximal and thin mean. Okay, the definition is P, it's the set of X, so X is I'm conflating infinite binary sequence with subset of the natural numbers. So think of X as a subset of the natural numbers. Right? P is the set of X such that X can compute a linear ordering of the natural numbers, which is isomorphic to the ordinal at which X is constructed. Okay, so this X can compute a representation of an ordinal, and that ordinal is big enough so that if you run Gödel's construction, that ordinal length, you see how X was built. So X has a way, it knows itself. Right? It knows where it came from. Right? It can compute how long a well-ordering you need in order to build X up. Okay? So that's P. Okay? So yeah, go ahead.
So how do you define X can compute the sequence of integers?
Yeah, so I'm thinking of X as a subset of the integers, and you have an algorithm that can refer to X.
Okay, so
right? You use X as a
X is an oracle.
correct. X viewed as an oracle. Yeah, there is a Turing machine such that if you supply it X as an oracle, it tells you a binary relation on the natural numbers, which is isomorphic to the ordinal which X is constructed. That's P. That's P. Okay. Okay, so this set was investigated in the 70s. Independence is one of those three people get credit, but they never talked to each other about the theorem. They all did it independently. So the theorem is that X is the maximal thin pi-1 set. So pi-1 we already know, right? That's an effectively presented coanalytic set. Thin means it has no uncountable closed subset. Okay? Right? There's a theorem of Cantor that says if I have a closed set, that set has a canonical decomposition. You can write it as the union of a countable set and a perfect set. Perfect set is a non-empty closed set with no isolated points. So a perfect set is some kind of isomorphic copy of the full Cantor set. Right? And a countable set is what it is. Okay, so that's Cantor's theorem. Every closed set can be written as, if it's either countable, or it can be written as a countable set together with a perfect set. Okay? So a thin pi-1 set is a set that has no perfect subset. Okay? The only countable subsets that it has are countable ones. Okay, like every singleton is a closed set. Okay, so it's got lots of singleton closed subsets, but it doesn't have any closed set that has any capacity. It's all of its closed sets are just countable union of points. Okay, so now a way to see this is X belongs to, so how do we see it's pi-1? Right? Well, here's a way to phrase membership in X, right? As looking like it's pi-1. So what's happening? So X belongs to P if and only if X can compute the height of This is a heuristic. It's not compute the whole structure, it can compute the height of. The height of a structure, which satisfies the condition that it was built up, it's internally constructed by a recursion that follows the definition of iterated first-order definability to generate the constructible sets. And this structure is well-founded. Okay? So being well-founded it says there's no infinite descending sequence in the epsilon relation, in the membership relation. Okay, so there's something that is intrinsic to X, which ends up having a pi-1. The thing that you have to check is pi-1. Okay, so it's a bit more sophisticated from this because you have to go from the ability to get the height of the structure to get the structure. But that's why it's a theorem and not an observation. Okay, so there's some work to do it, but the main thing is that X has something in it that will allow X to generate an initial segment of L in which X appears. Okay, the second fact, this is thin. P is thin because that's also a theorem. But it has no perfect subset. Okay. Now there's this last observation is the one that is relevant for us, right? Which is if every set is constructible, then this set is not countable. And in fact, if every set is constructible, then every element of the Cantor space, every subset of the natural numbers, is computable relative to something in P. Okay? So this fact is sort of embedded in sort of the detailed analysis of how L works. And to give you a something to motivate why that's true, or some way to, yeah, go ahead, a question?
Yeah, so we're using how many ordinals here?
All the ordinals.
So there's quite a lot of them, right? And
There's many of them, yeah.
yeah, so I'm thinking, so in construction of P, we are using some representations of binary sequences, and you can have only, so many representations, like continuous. So there are some sets that have...
You're right. You just duplicated Gödel's proof of the continuum hypothesis in L. Gödel had to show that if a real is constructible, then it's constructible at a countable ordinal. So that's Gödel's theorem, that if there's lots of ordinals, and you might think about, well, at which ordinals do you get real numbers? At which ordinals do you get subsets of omega? And Gödel showed that every subset of omega is constructed at some countable point. Once you get past all the countable ordinals, there's no more reals that show up. So you don't have to go through all the ordinals and keep getting a new subset of omega, a new subset of omega. You get all of them at some countable point in the process. Right? And then at each countable level, if alpha is countable, this whole business is countable. And so the set of reals is a size omega 1 union of countable sets. It has size omega 1. So that was the core of Gödel's proof of the consistency of Cantor's continuum problem. Right? That's exactly how it works. Right? And then a finer analysis says that this process behaves somewhat like the arithmetic hierarchy. It extends the arithmetic hierarchy through the transfinite. And at every step along the way, you're iterating what's definable. That means you're looking at the existential quantifier over the structure you've got so far, which is strongly analogous to just iterating the halting problem. The halting problem is the canonical existential predicate. There exists some finite thing that makes something more concrete happen. Right? That's, there exists a computation that makes this algorithm halt. Right? So Gödel's universe of sets is iterated application of the existential quantifier over what you've got so far. And there is a version, right, of the halting problem. At each time you go up, you can look at the truth predicate. What was true? Right? How did all these definitions work? What's the universal account of the blueprint of how this all works? And whenever L alpha is countable, whenever alpha is countable, L alpha is countable, and then there is the complete account of how definability worked all the way up to alpha. Right? That's some countable information. Right? Mushing that all together gives you a universal set, right, for that level of constructability. Those things are called, I know it's kind of grand, but this is what they're called. Those are called the master codes. So the master codes give you a collection of reals which keep account of all the stages of L. Right? And everything that's constructed is computable from some master code, because the master codes are keeping track of everything that happened up to the point where X got constructed. So the master code knows about X. Okay, so there's a canonical, and the master code knows about everything all the way up to L alpha, but everything all the way up to L alpha is basically an element of L alpha plus 1. Okay, so the master codes can compute the ordinals at which they are constructed. Okay, so that's this comment. Okay, so that's how the universe of constructible sets works. Okay, it's iterated definability, and then looking at the universal objects along that iteration. It gives you real interesting. Gödel in the 30s made tremendous use out of it to settle Hilbert's first problem and so on. But it's like the gift that keeps giving, right? There's always yet another interesting thing about this canonical model. Okay, so let's prove, right, that if V equals L, if all sets are constructible, then the dimension, the Hausdorff dimension of this coanalytic set P, effectively presented coanalytic set, is equal to 1. It has full dimension. Okay, so P is this set, right? P is the set X can compute a representation of the ordinal at which X is constructed. Right? I want to see that the dimension of P is equal to 1. Okay. Remember, P has no uncountable closed subset. Right? That means its closed subsets all have dimension 0. Okay, so this is as far as you can, this is completely the antithetical to capacitability. It has full dimension, but all of its closed subsets are countable. They all have trivial dimension. So the dimension of P is not carried by any of its closed subsets. Far from it. Okay, so coanalytic sets are capacible is just completely not true in L. Okay, so let's see. Good. That's the comment I just made. Okay, so let's see the proof. Okay, let's immerse ourselves in Gödel's constructible universe, right? And let's try to estimate, right, the dimension of P. Okay, so step 1. Step 1 is there's an infinite computable set of natural numbers such that for all B and for all X, if X is Martin-Wolf random relative to B, okay, so there is this set S, right, such that no matter what oracle you take, no matter what B you take, if you take a real that's random relative to that oracle, right, and change its values on S, then you get a new thing, Y, such that the effective dimension of Y relative to B is equal to 1. Okay, so let me draw a little picture here. Okay, so here we have, here's this, what should we do? Here's X. Okay, X is Martin-Wolf random. Okay, so that's not a harmonic function. It's meant to say, that the values are 0 or 1 randomly. Okay, so that's X. Now, here's this set S. S is you can take S to be something like the iterated exponents of 2 to the 2, 2 to the 2 to the 2. Something that a fast-growing. The enumeration of S is a fast-growing function. So here's. Oops, I don't want that. Oops, I don't want that either. Okay, I'll use that. Okay, so here is an element of S. Here's an element of S. Up here is an element of S. This is a place in S. Okay, now take X and alter it. Alter it to get Y. So it looks like, and now we've got some new thing here. And then we've got, no way I can get this thing. Oops, and then we've got some new thing there. Okay, and then so on. So that's Y. Okay, this is the changes to get Y. Okay, now, look, if X is Martin-Wolf random relative to B, that's the same as saying you can't compress the information in the initial segments of X by anything more than a constant, right? The Kolmogorov complexity of X up to here is, this is, say, the first L bits. That thing has Kolmogorov complexity relative to B, L minus a constant. Okay, it's completely incompressible. Now, suppose that I take that thing that's completely incompressible, right, and I change it here and here and here. Right? how compressible is the obtained sequence? Well, it might be very easy to describe what's happening at these red points. You might be able to compress that away. Maybe it's 0 at all those points. Right? But you can't compress any of the blue stuff. Right? The blue stuff is random. Okay, so the amount of compressibility you're going to get is at most the amount that x could be compressed, which is a constant, so we can basically forget about that. Right? The amount that x could be compressed plus the number of points at which you made a change. That's the most you could compress that down, because these blue squiggles are incompressible. Okay, so now if you've made it so that this S is a very thin set, right, then in the limit, the number of points below L, right, that belong to S, right, written as a fraction of L, you can send that to 0 by making S very sparse. Okay, so you don't change the dimension. This is random. This point is going to have effective dimension 1. This is random relative to x. This has effective dimension 1 relative to x. Okay, good. So that's step 1. There is a recursive set, right, like the iterated exponential, such that you take a random rule, you can do whatever you want on that recursive set, and you get something of effective dimension 1. Okay, good. Good, we've checked it. All right, now, step 2. And to tell what the dimension of that set P is, it's enough to look at, for every oracle, so here I did it for Z, for every Z, there is a Y that's in P, such that the effective dimension of Y relative to Z is equal to 1. Right? That'll show, right, that the Hausdorff dimension of P is equal to 1. Right? That's the Lutz theorem, that you can give a analysis of the Hausdorff dimension of a set by looking at the relative effective dimensions of the points. Right? If for every Z there is an incompressible element of the set relative to Z, then the set has to have dimension 1. Okay, so now step 3. Suppose that we're given some oracle, right, B. Right? Take something that's Martin-Luff random relative to B. Okay, now we want to get something. We want to use what we said before to get something inside P, right? That is incompressible relative to B. So we're going to take this thing that's random relative to B and manipulate it. Manipulate it to get somebody inside P. Okay, so take some point take some M, right, such that M is in P and it can compute X and B. Okay, so this is, remember the elements of P, we're immersed in L. Every real, right, pair of reals, right, is computable from some element of P. Okay, so let's take an element of P that is so complicated, has so much information in it, that it can compute X, right, that random thing. It can compute B, the thing relative to which X is random. Okay, so M knows about the challenge that B is presenting to P's having dimension 1. Okay. Then what? Then let's let Y be the result of changing the values of X on the elements of this sparse set and replacing them by the values of M. Okay, so we're going to take the random real, and then on this computable subsequence, we're going to copy M. The resulting set, right, has the property that it can compute. So Y is the result of doing this replacement. What can Y compute? Well, the places where we put M is computable. So Y can compute M. So Y can compute X. Right? Y can compute B. Right? Y can compute itself. Right? Because it knows how it was built, right? It knows that it was built by taking X, right, and replacing its own bits by m. Okay? Now m can compute the ordinal at which m is constructed. M can compute, at that ordinal, m can assemble itself. Right? But m can compute x and b. So m can assemble y. So the ordinal at which m is built is the same as the ordinal plus 1, say, right, at which y is built. Okay? So y can compute the ordinal where m is constructed, so y can compute the ordinal where y was built. Right? M and y are interchangeable. Each can compute the other. Right? But m has the feature that m can compute the ordinal where m itself was constructed. And if y is equivalent to m in that sense, right, y can compute the ordinal at which m is constructed, but that's the ordinal at which y itself was constructed. Okay, so y is in P. Okay. That's it. Right? So this kind of computational point of view, right, gives you access, right, to aspects of dimension which don't show up if you're thinking about dimension as, you know, the dimension of a curve in the plane. Right? You're thinking about dimension as a characteristic of the complexities of the points that are in the set. Right? It's not the global, you know, it's a spiral in the plane as dimension 1. It's not the global geometry of the set that's running this. Right? It's the complexities of the points that belong to the set, and those can be measured by intuitively algorithmic terms. Okay, good. That's it. That's the proof. Once you have all that machinery available, right, it opens up a different way of analyzing these kinds of concepts. Right? And there, the proof is pretty, short. Okay, so any questions about that? Anybody think it looks interesting? At least I do. It's, clearly. I think it's interesting that things that are, I think that there's a kind of interdependence between mathematical ideas. Right? And every mathematical tradition, right, has, if it's fundamental enough, if it's based on some kind of fundamental way of thinking about things, right, it allows for investigation into almost any part of the mathematical realm, any kind of quantitative thinking. Right? You can take the point of view, I'm interested in how things are built up and how they are described and that kind of fundamental aspect of the nature of those objects. Right? And you can take that kind of curiosity and apply it here or there, apply it to geometric things, apply it to statistics, apply it to analysis of how are you going to understand any kind of quantitative situation. Right? And so if you have a particular point of view, algebraic or analytic or computational, logical, metamathematical, you can apply that perspective, and if it's a rich enough thing, right, it will illuminate whatever subject that you're applying it to. Right? And some things that are very naturally seen from one point of view might be difficult or even invisible, right, from another point of view. And so it is with this. It's aspects of geometry, that things that are typically thought of as geometric, right? They reveal something when you think of them as more algorithmic. Okay, so that's that. All right, there is a counter view. There's a view that's, I'm just going to quote this theorem. There's a view that's a metamathematical view, models of set theory which are quite different from the universe of constructible sets. So the universe of constructible sets is a minimalist view. You only have the sets that you necessarily have to encounter, the ones that can be built up by simple operations along the ordinals. There's other meta-mathematical views which lead to other sort of models of the axioms of set theory. This models of the axiom of determinacy, you could also think of, since the axiom of determinacy can in large part be deduced from the existence of strong closure points in the universe of sets, you can also say these are models in which large cardinals exist. In those models which are extremely rich in the existence of sets, right, they have exactly the opposite behavior to what happens in the universe of constructible sets. There's this very nice paper, recent paper by Krohn, Fishman, and Jackson, which, assuming that they're in one of these very rich models, so let's be concrete. Assume that large cardinals exist, and let's suppose that we take a set that is analytic. It's sigma 1n for some n. Okay? Then it's capacitable. Okay? Namely, if you have a subset of the d-dimensional Euclidean space, and you have any delta which is possible as a dimension of some subset of this space, either A has a compact subset, so not just closed, but compact, bounded, totally bounded, such that the dimension is greater than or equal to D, or the dimension of A is less than or equal to D. Okay, so if A has dimension D, then A has to have a compact subset that has dimension D. Okay, so the question about capacitability, right, engages with the large-scale structure of the universe of sets. Capacitability just for co-analytic sets engages in the large-scale structure of the universe of sets. That's, to me, a rather surprising fact. And the proof is quite a nice mixture of ingredients from set theory and ingredients from geometric measure theory. It uses a fair amount of analysis of how Hausdorff dimension works. So it can go either way. It can be the case that dimension exhibits high levels of regularity, or regularity could just crash right away. But it's to the credit of the people that were working in the 1950s. Right? They proved the optimal theorem. If you're just trying to prove as an absolute theorem, right, capacitability for some class of sets, they proved it for the largest class of sets, such that it's true as a fact on the basis of the usual axioms of set theory. Okay. I'll give a second example, and then we'll take a break. Okay. So here's a second example of how things work in L again. Okay. So here's a theorem of Marstrand. So suppose you have a subset of the plane, and it's analytic, right? So again, there's this. It has to be a simply described subset of the plane. Okay. Then, for almost every angle theta, right? Take the line that makes the angle theta with the horizontal. Okay, and look at the projection of the set onto that line. Okay, so you have some set here. Here's the set, subset of the plane, so there's E. Okay, and here's the line. This is the line that has line with angle theta. Okay, now take the projection. Take the shadow, right? Look at the projection of that two-dimensional set onto the line. Okay? Marstrand's theorem says if the dimension of E is greater than 1, right, then the measure of the projection is positive. For almost all, you could have you could have that the set, well, in any event, you could have countably many lines such that the projection is small, but for almost every angle, take a random angle, the set is going to project to something of positive measure. Okay, so for almost every angle theta, right, the dimension of the projection onto the line, if E has some dimension in the plane, if E is not a line itself, if E has a little bit of, it doesn't have to have area, but it has to have some dimension bigger than 1, then on every angle, right, the projection has positive measure. So on every angle, it projects to something of dimension 1. So it's big. It's big in every direction, except for a null set. Okay, so that's Marstrand's theorem. Okay, in joint work with Stuhl, we showed that for every S in the interval from 0 to 1, there is a pylon 1 set such that the dimension of the pylon 1 set is 1 plus S, so it's bigger, a bit bigger than 1, but the dimension onto the line with angle theta is equal to S for every angle. Okay, so this is a weird example. Right? It's an example that has, so let's take S to be a half. Right? You can get a coanalytic set, right, that has the property that its dimension is 1.5. Right? But for every line, if you project that coanalytic set to the line, and you get something that it's not a positive measure. Right? In fact, its dimension is a half or less. Okay, so you can get a coanalytic set that in the plane, right, has as close to dimension 2 as you want. But every one of its shadows, its shadow in every direction, right, does not have dimension 1. Its shadow in every direction is small. So it's an interesting counterpoint, right? And to what happens on the analytic sets. And again, it looks this even more than the other thing looks like geometry. Right? It looks like, oh, we have this set, and I'm looking at all of its projections. That's some kind of two-dimensional geometry. But how do you analyze it? Well, you analyze it using this kind of analysis of the complexity of the points and a sort of algorithmic point of view. So it's an interesting intrusion of one set of ideas into a realm that typically was occupied by people with a different set of ideas. Okay. There's a third example here that I was going to talk about. Why don't we take a break and then we'll come back to it. Okay. Okay, so now we're going to come to our last topic for this sequence of lectures. And this is I want to talk about what are called gauge functions. And this is just to generalize and refine the concept of dimension. Right? Dimension is defined, as we saw, it's defined either by this kind of compression analysis, or if you look at the original definition, it's defined by assigning measure, some scalar of the diameter of a ball, and it gets measure associated with some if it's a subset of the plane, the Lebesgue measure gives a basic open ball, something of a measure of size that's proportional to the radius squared of the ball. You instead of using the square, you can use any power between 0 and 2. If you use power 1, that's linear measure, right? And it's going to make lines have positive measure, and things that are like compressible by a scale of a half, those things all have measure 0. Okay, so you can, as you change the exponent that you use on the diameter of a ball between 0 and 2, you get a ramification of different notions of dimension. Okay? The different outer measures pick out different classes of sets as having positive measure. Okay? But there are a lot of other functions between any, if I have S1 that's bigger than S2, there are lots of functions that are dominated by, that sit in between. They grow faster than the smaller function, and they grow more slowly than the bigger function. We want to include all those possible functions in our analysis of measure. So that's where this notion of gauge function is. Right? It's to extend considering something like t goes to t to the s, where s is, now we'll think of it as a subsets of the line. Right? If s is a half, right? T goes to t to the half was associated with the measure that looks at compressibility by a factor of a half. Okay, so a gauge function is a generalization of a function like this. What is its property? It's continuous, it's increasing, so the bigger the radius of a ball, the bigger the measure it's going to get. And as t goes to 0 from the positive side, h of t goes to 0. So as the radius of a ball gets smaller and smaller, right, its size is as measured by h is smaller and smaller. So gauge function is just a way to sort of describe size according to scale. Okay, then, for any gauge function, this is exactly the same definition that I gave for Hausdorff measure, right? Except I'm replacing, take the diameter of the basic, these FIs are these open balls. So you take, instead of taking the basic open sets as having size d to the s, you take them as having size h of d. Okay, these are f is a sequence of basic open sets, and d of f of I is the diameter of f of I, and I'm assigning to the ball of this diameter a size given by h. And then you take the limit as the scale goes to 0 of the optimal open covers. Right? That gives you the outer measure. Just like Hausdorff measure, except we're looking at a wider class of functions. So that's gauge measures. And when h of t is, when the gauge function is just the exponential function, this measure we've defined is exactly the s-dimensional outer measure, right, that we've been talking about the past couple times. And gauge functions come up. For example, in analyzing what's the dimension of the path of a Brownian motion, right? With gauge, so logarithm terms, they can capture logarithmic effects that are lost when you're only thinking about powers. Okay, so gauge functions can give you a sharper resolution on what the size of some object is. Okay, so there's an ordering on gauge functions. The ordering, so unfortunately, and it's unfortunately for me, maybe you all can do better than I can. Unfortunately for me, this is the ordering that's in the literature, and it always confuses me as to what it means for H to be before G. Okay? So what does it mean? It means that the limit, as t goes to infinity, 0 from the positive, so as in the limit as the scale gets smaller and smaller, G is smaller than H, okay? By some kind of better than multiplicative factor. Okay, the ratio between G and H is going to 0. Okay, so H comes before G means, unfortunately, that H is bigger. But I mean, we'll see why the geometric measure theorists use this order shortly. But you could think of it this way. if G is bigger, it's easier. It's easier to be G, to be a null set from the point of view of G. Right? G is putting a smaller mass. It's easier to be G null. Okay. And like I said here, so this I personally find confusing. If H is less than G, then actually H of T is larger than G of T as T goes to 0. Okay, so example. This is the dimension of the Cantor middle third set. Right? When you look at the Cantor middle third set, its outer measure is positive. If I look at this gauge function, it's 0 if I look at that gauge function. And clearly this ratio goes to 0. Okay. All right. Some of the things that are true about Hausdorff dimension, right? So now a Hausdorff dimension only partially had the properties of Lebesgue measure. And Hausdorff measures were not fully capacible, Lebesgue measure is. Right? Some further things do not generalize from Hausdorff dimension to dimension for these gauge functions. So let's see. Okay, so remember, I'm putting this there because I always get messed up myself. So there again is the definition. And what have we got? So what's similar? If the outer measure with respect to H is finite, and G goes to 0 faster than H does, right, then the outer measure of A relative to G is 0. Okay, so if this set does not, is good enough. If it's not super large when measured by the gauge function H, then it's negligible, right, when measured by any gauge function that's stronger than H. So remember how Hausdorff dimension worked? Everything was infinite, and then there was a drop, and everything was 0. Okay, so to some extent, that's true here. Once a gauge function gives outer measure finite, after that, everything drops to 0. Secondly, if H says that this measure is not 0, then anything that goes to 0 faster than H, right, gives this set infinite outer measure. Okay, so if the set is not negligible with respect to H, then it is really large. In a sense, we'll see shortly it's really, really large, but at the moment it's really large for any J which is sort of weaker than H. Okay, so that's similar to Hausdorff measures. Here's a difference. Okay, so Besekovich, a lot of this early work in the 50s and 60s, Besekovich in England was sort of the center of the galaxy at that time for this kind of investigation. So here's a difference. Besekovich showed that if a gauge function H says that A is null, right, then there is a J such that so what does it mean for H to be greater than J in this sense? It means that J goes to 0. We got H, J. I should have used these same letters. The ratio of H over J is going to 0. Okay, so that means that J is a little bigger than H. So J is assigning greater mass at smaller and smaller scales, but nevertheless, if H thinks it's 0, there's somebody that is a little bit before H, which also says that the outer measure is 0. So if a gauge function, there isn't a sharp boundary. If a gauge function says A is null, right, then you could assign you could assign mass, right? and have the mass shrink to 0 a little more slowly and still end up with A being a null set. Okay, so it's fuzzy at the boundary. And if it's fuzzy around this phenomena, right? H can't be, in any sense, the absolute dimension of A if H is giving A measure 0. And so that's unlike what happens in Hausdorff dimension. And if a set is null, it's null. If a set is null at H, well, it's null a little bit earlier than that. Okay, but look, let's also see something here. This is sort of similar to so maybe this is the motivation for choosing the ordering to look like this. Right? Remember how Hausdorff dimension worked? The dimension, if I looked at dimension S, then a set A looks like it has infinite measure, and then there's a place where it drops and it's measure 0 ever after. That's this kind of situation. Right? So as the gauge dimension is going up, once you see a gauge dimension is finite, after that it's 0. Okay, so this is an analogy to the way that Hausdorff's dimension is working when we're taking the dimension to be a real number. Okay, so good. But there is something a little fuzzy around the case where the measure is equal to 0. That can't be the absolute dimension. Okay, I said that here, if little h says that if little h says that A doesn't have 0 measure, then anybody that comes before little h has to say that A has large measure. But in fact, it has really, really large measure. So this is definition. What does really, really large mean? Okay, so a definition. A set A is sigma finite for that measure if and only if it's a union of sets such that each set has finite size for that measure. Okay, so for example, if I look inside the plane, right, and I take a countable, let's take an even easier example. Look at the real line. Right? The real line has a decomposition into subsets such that each subset has finite linear measure. Right? Take the real line and break it up into the integer bounded intervals. Right? The real line is the interval from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 0 to -1, -1 to -2, and so on. There's a countable decomposition of the real line into sets, right? And each set has finite area. I mean, not area. Each set has finite measure. The measure of an interval from 0 to 1 is 1. Okay? So you can take the real line, and it has infinite measure, but you can break it up into countably many pieces. Each piece has finite measure. Okay? That's called being sigma finite. And sigma for countable, finite for each piece in the countable thing has finite measure. So that's sigma finite. Okay, then here's a improved observation. Right? If H says that A doesn't have 0 measure, right? Take anybody that comes before H. Right? A is supposed to have infinite measure, right? According to the previous slide, but in fact, A has non-sigma finite measure. So if you have even in the case of original Hausdorff dimension, suppose we have that canonical set that has Hausdorff dimension 1/2. Right? Make all the odd bits equal to 0. That set cannot be written as a countable union of sets, each of which has Hausdorff dimension 1/4. Another example, right? Take the plane, it has dimension 2. It cannot be represented as a countable union of lines. This is a generalization of that fact. right? You take the plane, you can't cover the plane as a countable union of straight lines. Right? That would be a countable union of sets of dimension 1, right? But the plane is not sigma finite for the gauge function t goes to t. Right? It's a union of countably many things that are it's sigma finite for the gauge function t goes to t squared. Right? But it has dimension 2. It's not sigma finite for dimension 1. So this is a you could think of it as a generalization of the fact that you can't fill space with countably many planes. You can't fill the plane with countably many lines. You can't build up dimension by a countable union of things of smaller dimension. Now these are examples of measures and sets that, examples of measures such that the measure of the whole space is not sigma finite. Those are sort of oddball examples. The Hausdorff, the examples I just gave with the Hausdorff measures are sort of the canonical examples of measures that are not sigma. I mean, you can construct them in different ways, but if somebody's looking for a natural example, the thing that's always provided is the Hausdorff measure. Examples of measures that are not sigma finite. Okay, so how about examples of interesting definable sets, interesting sets, so that those sets have a certain Hausdorff dimension and they're not sigma finite for that dimension. Okay? All the examples that I know come out of these sort of descriptive sources. Okay, so here's two examples. The first example is if I have a number between 0 and 1, look at the set of x such that the effective dimension of this is in the standard Hausdorff dimension realm. Look at the set of x such that the effective dimension of x is d. Okay? So we know what that means, right? It means that it can be compressed down to the scale. For everything that's bigger than d, you can infinitely often compress its initial segments by that factor. Okay? That's this set. Okay? That set, you can prove, has Hausdorff dimension d, though we observed that already, right? That the set of things that were compressible at most to d, right, has full dimension, but even better, right? Not only does it have dimension d, which means its HD measure is not 0. Well, its HS measure is 0 for everything bigger than d, but in fact, it is a very large set of dimension d. It has exactly dimension d, and it's not sigma finite for the Hausdorff outer measure on d. Okay. So that's this one. Second example comes out back to this kind of classical metric version of Kolmogorov complexity. Right? The set of Liouville numbers. So remember, a Liouville number is a number that its exponent of irrationality is infinity. It has arbitrarily good rational approximations. For every k there exists p and q, such that p over q is within 1 over q to the k of the Liouville number. Okay. The set of Liouville numbers is not sigma finite for every h such that h comes before all the power functions. Okay, so if I take an h that sort of goes to 0 faster than any power, right, then the set of Liouville numbers is not sigma finite for that h. Okay, so what would you say is the dimension of the set of Liouville numbers? The set of Liouville numbers has Hausdorff dimension 0 for every d, but every gauge function that's below all the power functions, right, makes the Liouville numbers look non-sigma finite. Okay, so that's an exact calculation of the extent of the Liouville numbers. Right? It has dimensions smaller than any, it has Hausdorff dimension 0, but it has gauge dimension infinite for everything that's among the dimension 0 sets, it is as thick as is possible. So it's an interesting, the gauge functions let you see some insight into things that the Hausdorff dimension gives you insight into sets that have measure 0. Gauge functions can give you insight into sets that are intermediate between dimension, or sets that are below all the positive Hausdorff dimensions. And there are interesting sets like that. But notice, both of these definitions, right, I wouldn't say that either one of these things is a geometric definition. Right? It's a definition about qualities of the points. It's a property of the points, which is determining whether they belong to the set, rather than it's some spiral curve or a thing like that. And these kind of descriptively defined sets, point-wise defined sets, seem to be the rich source of examples. All right, so the problem to produce examples of things that are not sigma finite, being not sigma finite is an awkward concept to work with. It's hard to analyze measures on sets that are not sigma finite because, well, if I have a probability measure, right, and I look at a set, right, I can think of it as, well, the set has a certain size, its complement has a different size. What's the probability of being in the set? What's the probability of being out of the set? Right, those are number quantitative properties. If it's probability a half you're in the set, okay, then it's probability a half you're out. Right? And you can analyze the way that things work because you can, as you divide the set up, you divide it into smaller pieces of smaller and smaller probability. The measures get smaller and smaller, etc. But here, there's this non-sigma finite means it's very difficult to divide the set up into smaller pieces. Right? It's sort of just gigantic. Right? You can't exhaust the set by breaking it up into cases and analyzing them. It's I don't know. Every time you try to use it, right, and break off a piece and understand it, like what remains seems to get bigger. It reminds me of a movie from the 1950s, which I recommend if you haven't seen it. It's called The Blob. So the Blob was a creature from outer space, which anytime it interacted with anything, it got bigger. So of course that causes trouble for the people that engage with it. So that's sort of what happens with these non-sigma finite measures. And anytime you try to analyze them and take them apart, well, they just look more. It looks more indecomposable. Okay. I don't know. This is an interesting problem. I don't know any kind of point to set and analyze some aspect of the points in the set, or some kind of quantitative way to put together an examination of the points, right, and conclude that the set has non-sigma finite measure. That's I just don't know how to do that. It's a nice conceptual problem. Okay, now, I want to concentrate on a certain kind of set. Okay, so we're going to define a set has strong dimension H, means that if I look at things at F that come before H, the outer measure of E is equal to infinity. It has this Hausdorff-like picture, but it's not only talking about the gauge functions given by powers, right? It's talking about arbitrary gauge functions. So F to the left of H gives E outer measure infinity. G to the right of H gives E outer measure 0. And then we're going to say that, and we're looking not at just the powers, right, but at all gauge functions. So we're going to say that E has strong dimension H if we have this precipice. Right? It looks like it has infinite size, and then it looks like it's null. Right? And there's a gauge function that is exactly at that cut. So that's strong dimension H. Okay, and I'm not specifying what happens for H itself. Okay, and then there's a limiting case. E is strong dimension 0 if it looks null for every gauge function. There's no gauge function at all that makes E look large. Okay. The empty set is an example of a set that has strong dimension 0. Okay. Examples, a line segment. A line segment in the plane has strong dimension 1. Which means, you look at the gauge function, t goes to t. Right? That gauge function has this property. Put that function, t goes to the identity function, in for h, and this property holds of the line segment. So there are instances, right? I mean, you would, if anything dimensionally is true, right? For arbitrary sets, it should be the case, right? That the dimension of a line is 1, no matter how finely you analyze it. Right? A line should have linear extent, and not more and not less. If this were not true, you got to change the definition. Something's wrong with the definition. Okay, so a line segment in the plane has strong dimension 1. Okay, then. Now we're going to look at again this business about how does this notion of dimension work, right, on sort of arbitrary sets, and then there's a theorem from the 50s, right, that says that for concretely specified sets, right, these notions of dimension, right, capacitability, the existence of a strong dimension, and so forth, behave well. They conform with kind of geometric intuition. Okay, so if E is compact, okay, that's a very simple. I mean, this was done in Euclidean space, but we can think of it as being done inside. It's true in a variety of spaces. If we look inside Cantor space, that just means E is closed, because Cantor space is a compact space. Okay, so if E is compact, and it's not sigma finite, so it's really large with regard to the gauge function h, then there is a G such that G is to the right of h, right? And E is not sigma finite for hg. So that says that if you were looking for a set that has strong dimension, if I wanted a set that has strong dimension h, right, and that set is closed, right, then the set that's supposed to have strong dimension h has to be kind of small when viewed from the measure given by the gauge function h. It can't be really, really big. Right? It can't be non-sigma finite. Right? It has to be a union of things that have finite measure, a countable union of things that have finite measure, because otherwise, you could find something off to the right so that E still looks large. Okay, so for concrete sets, if you're going to try to identify the measure of the set, it has to happen at a place where the set looks relatively small. Okay, so there's a constraint. There's a constraint for compact sets such that on how they can work at the site of their dimension. So a line in the plane has strong dimension 1. It is a closed set. I could look at a segment of it. It still has dimension 1. That's a compact set. It has strong dimension 1. But it is, sigma finite. The line is sigma finite, can be broken up into countably many things of finite linear dimension. Linear measure. Okay, so, and that's necessary by this theorem. Okay, now, to go from compact, right? So that's sort of the simplest kind of subsets that we're talking about. There's this theorem. If E is analytic, okay, so now it's the analytic case. Again, that's sort of the upper bound on what people can deal with. So if E is analytic and it's not sigma finite for this measure, then there's a compact subset of E such it's not sigma finite for that same measure. Okay, so for analytic sets, right, if the analytic set is not sigma finite, right, that, in other words, it's very, very large from the point of view of the gauge function h. If the set is very, very large and it's analytic, then it has a compact subset, which is also very, very large. Okay, so the non-sigma finiteness of an analytic set is supported by the non-sigma finiteness of its compact subsets. Okay, so if it's not sigma finite, there's a reason. If it doesn't have a sigma finite measure, there's a reason. Right? The reason is, here's a very concrete thing you can point to, and that thing's not sigma finite, and E is just some glitter around that compact skeleton. Okay, so then what was true here is true about analytic sets as well. Right? Because I go from E to a compact set that's not sigma finite to some G, so that compact subset is not sigma finite for G, but then E can't be either because measure is monotone. Okay. I don't know how to prove these things. Right? These are classical theorems. I don't know how to prove these things using the ingredients that we've been talking about so far. Okay, so I have not yet been able to retool all of this business and present it from the point of view of effective gauge dimension. So that's an interesting project, but I don't know how to do it yet. And it's because I don't know any kind of points to set. I don't know how to analyze non-sigma finiteness in terms of the points of the set. Because that was critical in the previous analysis. We got this effective treatment of, I understand the dimension of a set by looking at some computational properties of its elements. I can manipulate those computational properties, right, and come back to conclusions about the dimension of the set. That connection between the computational properties of the elements and the property of the set is missing. Right? It's a gap in the correlation between these two perspectives. Okay, now this is an interesting theorem of Besekovich, right? So the theorem previously, let's go back to this theorem. If you have an analytic set and it's not sigma finite, right? Oh, sorry, I'm doing this one. If I have a compact or analytic set and that set is not sigma finite for HH, then there is a G that's bigger such that E is not sigma finite for HG. Okay, so if a set is not sigma finite for H, right, and it's a concrete set, it's not sigma finite for H can't be the strong dimension. Okay, so that was only for, after the Davies theorem, for analytic sets. So Besekovich, in 63, gave an example. This is an interesting paper, right? He gave an example of a set, which is a subset of the plane, that has strong linear dimension. It means its strong dimension is given by the gauge function t goes to t. Right? And it's not sigma finite for linear measure. Okay, so he gave an example of a set that is not sigma finite at exactly its dimension. So it's really large for linear measure, but it's trivial for anything, any function whatsoever, right? Which is to the right of linear measure, this set looks trivial. Okay. So it's an interesting construction, interesting theorem. Another thing that I thought was curious about this paper is that he doesn't include this part. He just takes the continuum hypothesis as true and proves the theorem, proves it as a pure existence theorem. He states the theorem, there exists a set like that. And he does not refer to the continuum hypothesis at all in the paper, but he refers to another paper. And in that other paper, right, the continuum hypothesis is used to produce a set of the sort that he needs to run this construction. So I guess for part of the mathematical world at that time, the continuum hypothesis was just evident. So it's an interesting, it certainly confused me when I was reading it, because I was reading it and there's this part of the proof, and how do you verify this part of the proof? And I could do it if I knew the continuum hypothesis, but then when I went back, there's like a day or two where I was puzzled, and also I felt frustrated. Like if he could do it in the 1960s, why can't I do it now? And the reason was he was using the CH without saying so. Yeah, go ahead.
The question is, why would the line not satisfy this?
The line is sigma finite. You can break the line up into countably many pieces of finite measure. Right? So the line is an example of something that has strong linear dimension, but it's not really big. It's sigma finite. Yeah, so the line does everything, you're right, except for that. Okay, and then in contrast, another one of these situations, if you look inside L, there's I'm not the only one who ever thought about looking at what happens in L. Right, so there was some work by Erdos, Kunin, and Malden. Unfortunately, none of these people are not co-authors of mine, so I don't get a small Erdos number out of this. But there was work by Erdos, Kunin, and Malden on other kinds of properties of the continuum. If you combine this work with Besekovich's construction, you can prove that if V equals L, there's a pylon 1 set, coanalytic set, right, that has strong linear dimension and is not sigma finite for linear measure. Okay. So here's the proof. Right, so I'll show you a picture of how it works. Okay, so what in both cases, the Besekovich case, and then using the detailed way that L is constructed in the Erdos, Kunin, and Malden construction, what did they do? They took a small set here, A, is a subset of the plane. Okay, so here you have a small set, and then and here's 0 and here's 1. Right, and then the set A is, I guess I should make this axis go down there. The subset of the plane just looks like, for each element of A, take the horizontal line segment that goes from 0 to 1. Okay, so this one, this one, this one, this one. But A is small, but it's still got to be uncountable. Okay, so you have uncountably. Take a set that's small but not countable. So you have an uncountable union of line segments. Okay. So Besekovich's A was an uncountable set such that any open cover of the rationals is an open cover of A. Okay. So that's an unusual kind of set, right? It's uncountable, but no matter how, the rationals you can cover you could take a sequence of open balls so that the nth open ball is small, to take any function of n into the positive reals. And you can cover the rationals by a sequence of balls so the nth ball has radius, the value of that function at n. It's like the incredible shrinking sequence of disks. But A has the property, no matter how you shrink those disks, no matter how fast their radii go to 0, their union covers A. So the CH lets you build, the continuum hypothesis lets you build such a set. And you do it, you use the continuum hypothesis and the axiom of choice to build such a set. Okay. Inside L, Gödel proved the continuum hypothesis by the argument that we briefly discussed, right? And there's a definable well-ordering, right? So you can put those things together and duplicate the effect. You can build a co-analytic example of a set where it has just that same property. On the vertical projection is this set that is I don't know, I forget what the phrase that people use for this is, but it has this property that every open cover of Q is a cover for the set. Okay. So now, if you're analyzing the dimension of this thing, first, it has to have, it's not sigma finite, because there's no way to break up these uncountably many disjoint intervals into countably many pieces, such that each piece is finite. Right? So one of these, if I took a countable decomposition of this blue set, right, those pieces has to touch uncountably many of the blue lines on a set of positive measure. But an uncountable sum of positive numbers is infinite. Okay, so that's how the argument goes. Okay. And then for anything that's any gauge function to the right of linear, it's going to give this thing measure 0, because all these line segments are null with respect to anything that goes to the right of linear, and A doesn't contribute anything. It's tiny, because that's how the argument goes. All right, now I want to make the last part of this discussion ties this kind of question about dimension back to some earlier mathematical threads. So here's a concept from the earliest days of measure theory. Okay, so this is due to Borel. Okay, so a set has strong measure 0 means that for any sequence of positive real numbers, so no matter how, and think of that sequence as going to 0 very quickly. Okay? For any sequence of positive numbers, there is a sequence of open intervals, right, such that each interval has length less than or equal to Ci. We could take it to have length, if it's smaller, we could puff it out to have bigger length. So each of these open intervals has length epsilon I, and the set of strong measure 0 is covered by the union of those intervals. So strong measure 0 means for any way that you specify the size of the components of an open cover. Right? The first interval has to have size 1/2 to the 1,000, and the next interval has to have size, Ackermann's function of that, and so on. It goes to 0 as fast as you can imagine. So for any sequence that's shrinking, no matter how fast, you can find intervals of those sizes, and they cover the set. Okay, so that's a set of strong measure 0. Borel conjectured, right, so early days of measure theory, Borel conjectured that strong measure 0, if a set has strong measure 0, it's countable. So countable sets have strong measure 0. Just like I said, you could do it with the rationals. You can cover. Right? Just let the ith open interval cover the ith point. A point can be covered by an arbitrarily small balls. Just center the ball at the point. Okay, so Borel conjectured strong measure 0 implies countable. My favorite Polish mathematician, Sierpiński again, proved under the CH there is an uncountable set of strong measure 0. Okay, so that's an early application of set theoretic principles to sort of the structure, the measure, and topology of the real line. Okay, so CH implies that there's an uncountable set of strong measure 0. The question of whether you can just prove that there's an uncountable set of strong measure 0 was open, right, from there to there. right? And it was in the first examples of sort of in being the powerful technology introduced by Paul Cohen when he showed the independence of the continuum hypothesis. Right? That happened in the 60s. Between the 60s and the 70s, and continuing still, but there was an intense interest, right, in developing and applying Cohen's method so it was called forcing, Cohen's method of forcing, to go back through all the mathematical investigations where people had gotten stymied and see, is it the reason that you came up against being unable to solve the problem was the reason that the axioms, the properties of sets you were trying to use were insufficient, like we saw with this analysis of co-analytic sets. Right? That you just didn't have, it's like trying to prove that all groups are abelian. Right? You can't do that, right? Because there are non-abelian groups. Right? It's trying to prove that there's an uncountable set of strong measure zero, right? Right, from the axioms of set theory, is like proving every model of the axioms of set theory satisfies that property. Right? Okay, well, if that's not true, if there are models of the axioms of set theory which don't satisfy that property, well, trying to prove that property just using the axioms is not going to work out for you. Okay? So that's what happened here. Laver in 76 showed that if the axioms of set theory, and this is he showed it's consistent with the axioms of set theory that the Borel conjecture is true. Okay, so the Borel conjecture can go either way. For the Laver's the model, the way in which the Borel conjecture can be made true. This is an extremely fragile situation. It was a real piece of technical wizardry to put together the model of set theory which satisfies the Borel conjecture. In almost every model of set theory that people have investigated, the Borel conjecture fails. But it's consistent. Okay, connection with dimension. Right? Besakovich showed that a set has strong dimension zero if and only if it has strong measure zero. Okay, so the notions of measure, what happens for strong, remember what strong dimension zero means, it has dimension zero for every gauge function. Right? Strong measure zero says you can cover it for Lebesgue measure by arbitrary shrinking balls. Okay, so there's a connection there. The proof of this equivalence is quite specific. And so it doesn't generalize well. It's using sort of everything that it's got in the hypotheses. And so it proves the theorem and nothing else. Okay, so now, however, right, there's a different connection, right? So this says, right, if the Borel conjecture fails, if there is an uncountable set of if there's an uncountable set of strong measure zero, then there is a subset of the real plane which has strong linear dimension, right, and is non-sigma finite for linear measure. Okay, so if right, this Borel, if there is a set that's uncountable but super small for Lebesgue measure, then there is a set which is super big for linear measure, right? And it has linear gauge dimension. Okay? And the proof of this, the proof of it is exactly the same. Right? It's the same picture. The picture in the Besakovich proof and this other Kunin-Erdos-Malvin fact was you take a small set here and you put a bunch and you for each element of the small set you put an interval and you line them up in parallel. Okay, so CH let us get this kind of set. Any open cover of Q is an open cover of A. Right? A set like that would work. If I just put any set here that has strong measure zero, right? You can analyze that set and show that it's It has the right property. So if I have an uncountable set of strong measure 0, it fits perfectly as a set that's small but not countable. Right? And this set has strong linear dimension, and it is not sigma finite for that dimension. Okay, so that leaves us with a challenge. Right? So the challenge is, does the Borel conjecture imply that there do not exist H and A such that A has strong dimension H and A is not sigma finite? Okay, so we've got one direction. Right? Not the Borel conjecture implies that there does exist. Okay? So is it the case that if the Borel conjecture is true, right, then what happens at dimension 0 happens at every possible dimension? Okay? That's open. And it looks like one should, of course, go look at how Laver proved that it was consistent that the Borel conjecture is true, and then try to show that in the structure in which the Borel conjecture holds, you can analyze what's happening with all these higher dimensions. But even in that specific case, I haven't been able to figure it out. So I could use some help on that. Okay. All right, so the problem, what time am I supposed to finish? I don't want to keep you all, it's Saturday, I don't want to keep you all here against your will. At 1:15? Oh, good, I'll easily make that. Okay. All right, so I only have, as you can see, it's slide 74 and we end on slide 78. So we're almost to the end now. So the problem in analyzing this issue and trying to settle that question is the intractability. It's difficult to work with non-sigma sets that have non-sigma finite measure. Right? That's the issue. Like what does it mean to have non-sigma finite measure? Right? It's already complicated to say what the measure is. Right? The measure involves this inf over all these open covers. Now, to say that the measure is not sigma finite means that there's no way to decompose the set, right, such that for each piece, the measure is finite. So there's no way to decompose the set so that the pieces have finite measure. But this is an arbitrary set. So you have to look at an arbitrary partition. You have to consider arbitrary partitions of the set, right? Not open, not intersect the set with an open set or something concrete. You have to look at arbitrary partitions of the set into count away many pieces and analyze the measures of those things. That's a kind of complicated property. Right? There's a quantifier over arbitrary subsets of the reals. Right? That's intractable is a good word to describe trying to understand that kind of phenomena. So the issue is, can you simplify that? Right? Is it possible to take this problem and sort of simplify the analysis of it? Right? Is it sort of, how complicated is it to understand what it means for a set to be non-sigma finite for a particular measure? Right? Is there a simpler criteria? Right? You know. Okay. Yeah, so can we reframe the problem in simpler terms where the ingredients we have to work with are a lot more accessible? Okay. So that's a question, again, a question of representations. Right? Can we represent the problem in terms that are easier to manipulate, to parse? Right? Is it equivalent? Is it like a sequence of rationals has a limit, right, which says that there exists some real number so that the rationals get arbitrarily close to it, versus the sequence of rationals is Cauchy, which says, oh, the points just get close together. You don't have to say there exists some special thing that you never heard of before. Right? You can just look at the rational numbers themselves. So is there a simplification like that? Right? Okay, so that's the problem. How do you understand what it means for a set to be not sigma finite? And how complicated is that? Okay. So here's a case study. I want to just examine that on the simplest kinds of sets. Okay. So let's look at closed subsets. Right? Closed sets, that's pi 0, 1, effectively closed sets, effectively presented closed sets, a very simple, in this context, an easy object. A closed subset of the product of the Cantor plane. Okay, and linear measure. Okay, so there. If we look at the question for just having positive measure, the set of indices, so that's the set of pi 1, 1 definitions, right? For all n, some recursive thing holds, right? Of the initial segment up to length n. Okay, so if we look at all the definitions for pi 0, 1 subsets of the plane, to say that this definition describes a set of non-zero linear measures an arithmetic property. It's something that you can describe. So just by quantifiers, you don't have to talk about there exist countable things, et cetera, et cetera. You just have to say something about finite. Right? And the reason for that is that this, like we talked about with finding a path through a tree, the Cantor set is a compact set. Right? If you have an open cover of Cantor space, it's finite. It has a finite subcover. If I look at all the ways so a closed set consists of paths through a tree. Right? An open cover, right, would be a collection of ways that you leave the tree. Right? If every real number eventually leaves the tree, there's a finite level where every real number has left the tree at that point. Because if the tree is infinite, it has an infinite path. Okay, so that analysis, Koenig's lemma, right, tells us something about Cantor space. It's compact. This cross product of two compact spaces is compact. Okay? So when you talk about open covers, you can assume they're all finite. Okay, so the whole business of understanding, can you get open covers that are for every epsilon, for every n, there is an finite open cover that gives size less than 1 over n. That's all arithmetic. And you're quantifying over the natural numbers in finite sets. And so prima facie, on its face, right, you can express this property, right, just in finitistic terms. So you can express it arithmetically. So to tell that the linear measure is not 0, to tell that this thing has dimension at least 1, right, is an arithmetic property of this description of a closed set. Okay? So having non-zero measure, right, is in this context, right, simple. Okay? How about having non-sigma finite? Okay, so I'm going to let n sigma finite just be the set of indices for same pi 0, 1 subsets of the Cantor plane, which are not sigma finite for linear measure. Okay. The previous one, it would be non-zero. Right? Non-zero is a set of indices for things that have non-zero measure. Non-sigma finite is a set of things that have non-sigma finite measure. Of course, the whole space has dimension too. It's not sigma finite for linear measure. And so there are examples of things that are not sigma finite for linear measure. So here's the theorem. In contrast, the property of having non-zero measure is arithmetically definable. The property of having non-sigma finite linear measure, right, is sigma 1, 1 complete. It's sigma 1, 1 by looking at it. It's sigma 1, 1 complete. Well, I take that back. It's not sigma 1, 1 by looking at it. Right? It's at least sigma 1, 1. But what do you have to say? It's not sigma finite. You have to say, it's not even clear that it's sigma 1, 1. Okay, well, I'm going to get to why it's sigma 1, 1 in a second. Okay, but it is sigma 1, 1 hard. It's sigma 1, 1, you have to figure that out, and it's sigma 1, 1 hard, right? Which means it can't be arithmetically defined. Right? You can't reduce, it is just for closed sets, right? There's some work to show that you can express that as an analytic property, right? But it can't be expressed by anything that's simpler than that. So there's a big gap in the complexity of the two notions. The notion of having being not null, and the notion of being not sigma finite. Right? They are, the intractability of the not sigma finite is sort of explained by the fact that it is hard. You know, it's like being NP hard. Right? It's sigma 1, 1 hard. Right? Whereas everything we've been working on up to that point is finitistically definable. It's arithmetic. Okay, so there's a big jump in the complexity of the kind of problem that you're trying to analyze. So that explains, in part, why it's so difficult to work with. It's just difficult even to calibrate. Okay, so what's the proof that it's sigma 1, 1 complete? Here's an analogy. So when you analyze closed sets, closed subsets of the Cantor space, or closed subsets of this thing, there's the theorem that I already mentioned, Cantor's theorem. It says that a closed set is uncountable if and only if it has a perfect subset. Okay, so that gives you the means, right, to prove this theorem. The indices for pi 0, 1 subsets of Cantor space such that C is uncountable is sigma 1, 1 complete. It's sigma 1, 1 because being uncountable, which looks like for every map from the natural numbers into the set, there is a point that's not in the map. Right? It's not just one existential quantifier. Right? You can replace being C is uncountable with C has a perfect subset, so that the tree that represents, whose infinite paths are the elements of C, you can embed the perfect binary tree inside of it. Okay? That's an existential fact, right, about C. C is uncountable if and only if there exists an embedding of the full binary tree into the tree representation of C. Okay? So that makes it sigma 1, 1. Okay? Whereas on its face, being uncountable looks like it's not an existential fact. It's the negation of something. It says for all countable sequences of reals, there is an element of C. It looks like it's pi 1, 2. Right? But actually there's a reduction. Right? It's uncountable if and only if it has a perfect subset. Okay? That gives you that this set, the set of codes for uncountable closed sets, right, is sigma 1, 1. And then you have to show that there is a computable map that takes you from sigma 1, 1 sentences to descriptions of closed sets, right, so that the sigma 1, 1 statement is true if and only if the closed set is uncountable. That's the hardness part. Okay. That's one of the exercises. That's one of the hard exercises. But you can do it. Okay, then that kind of apparatus is what goes into the analysis of not sigma finite. Right? There is an analogous theorem to Cantor's theorem There's a theorem of Davy's from the 50s that says, and this was what was used in the proof, that analytic sets that are not sigma finite have compact subsets that are not sigma finite. Use this. C is a closed set is not sigma finite for a linear measure if and only if there's a perfect tree of closed sets such that each path corresponds to a closed set of positive measure. Okay, so you can take this set that's not sigma finite and you can break it up into two nice pieces that are not sigma finite. And then you can repeat. And you can get a perfect set such that and then you have to do some work to make sure along each path it doesn't shrink to zero. So you keep breaking it up into sets that are really, really large, right? So that the intersection along any path is not null. And so that was Davy's methodology in his proof, to show how to do that. And then, good, so this says now there is, and the way that the path, the way that you see, the way you maintain that the set that is obtained along each path has positive measure is something that you do constructively. So you do something at each step along the way so you know that the measure is not zero in the end. Okay, so you end up with, there exists a tree that along each path something nice is happening. That's a sigma 1,1 property. So that's the sigma 1,1 analysis of being non-sigma finite. So that looks good, right? You can figure out not sigma finite not by looking at arbitrary decompositions, but by looking at an embedding, right? An embedding of something concrete inside the set. Of course, we're only talking about closed sets here, but nevertheless, good. And then you show that this being not sigma finite is sigma 1,1 hard. And you do it by a similar argument as I mentioned for this exercise. Right? You have to, given a sigma 1,1 syntactic statement, right? You have to, by copying, right? Look how there might be some existential witness to the sigma 1,1 statement, and as you see that witness develop over here, you start to embed some kind of tree like this. When the witness stops, when the witness shows, I give up, I'm not a witness to this sigma 1,1 statement, well, then you have to stop embedding your tree and sort of thin everything out to null. And so you copy the way sigma 1,1 statements are true into this non-sigma finiteness in the same manner that you would do it if you were going to solve that exercise about Cantor's theorem. Okay, so that's a sketch of how things work, but it does highlight this case study does highlight that the difference between trying to identify whether a set is null, right? Is it null or does it have size? Right? That's a much simpler distinction to make than is it sigma finite or not sigma finite? Is it possibly large, but is it very, very large? Right? The second distinction which you have to make if you're going to analyze non-sigma finiteness is a whole type more complicated. Going from looking at finite things to looking at infinite things. So that sort of explains why it's harder to work with this business. Okay, and I should say, we gave two examples of places where sets were not sigma finite. Right? Well, exactly the way that we show that this set is not sigma finite, the set of things that have effective dimension D is not sigma finite for the d-dimensional Hausdorff dimension, and the set of Liouville numbers is not sigma finite for any h which is below all the power functions. In both cases, to prove that those sets are not sigma finite for those measures, we have to embed this kind of tree. Right? So knowing that and these examples weren't known before. Right? They come out the way to be able to analyze whether something is not sigma finite. Well, you want to know how complicated it is. Is it to check? What's the optimal description for what it means to be not sigma finite. Okay, well, we did that. We figured that out here. Right? It's sigma 1, 1, and it's sigma 1, 1 hard. Can't be better than sigma 1, 1. And it's sigma 1, 1, and this is how it's sigma 1, 1. So if you're going to prove some closed set is not sigma finite, right, you should try to build a perfect set of sets of finite measure. You know in advance it exists there. Right? If you're going to succeed, you know that that tree exists. And so if you want to prove some set is not sigma finite for a certain gauge function, try to build a tree like this. Right? The logical analysis says this is the optimal way to approach the problem. It's a sigma 1, 1 way to approach the problem, and that's the optimal description of the property of not sigma finite. Okay, so it's, in the end, the tree's going to be there, right? If you succeed in proving the theorem, right? And doing this is the least you could do. Okay, so try to do that, right? And that's what happens in these examples. Once you have the analysis, right, the sort of descriptive analysis of what's the optimal way to phrase a characterization of the property, well, that's the thing you try to do if you're trying to verify the property. You do the least you can to see that the property is true. Right? So having this kind of logical analyses of mathematical situations, right, leads you to the methods that you should use to try to answer questions about specific instances. Okay, so that's how these arguments go. Okay, so with that, thank you everybody for sticking with these lectures, and that's it. Except for the homework. Right? Let me say one thing here about the exercises. For the exercises, two things. Let's say problems number 1, 2, 4, 1, 2, 4, 6, 7, are to be handed in. 1, 2, 4, 6, and 7. So if anybody wants to submit exercises for this, it's 1, 2, 4, 6, 7. Okay, thanks everybody.